So tonight had a question come through email just about some things. So this relates to question, I believe, 9 in the assessment for this topic, just because it's a bit hard to find the specific information you're looking for. Cool. So current transformers. So we talked about them before, but we're just going to go over them because it relates to that question. So your current transformers, or CTs, they're used in installations that draw large quantities of current. Typically, revenue meter can handle anything up to 100 amps per phase. Anything more than that, you'll need to employ CTs to represent the installation's current draw, but reduce the value so the meter is capable of measuring it. They're called measurement CTs. CTs can also be employed to protect high current circuits by reducing the incoming current value to a level that can trigger a device that opens a larger set of contacts to interrupt the main supply. These are called protection CTs. We'll discuss the difference in construction and operation between these two types. No matter their application, CTs are designed to reduce current probability to the incoming supply. Cool. So bar type CTs. So bar type current transformers have a fixed primary circuit conductor bar molded into the body. This is ready to bolt across a gap in a bus bar. They also have a built-in secondary winding. They have a single primary winding producing an alternating current proportional to the current in the primary. The primary is usually connected to supply or load through busbar or conductor via P1 and P2, and secondary is connected to instrument or resistor to prevent open circuit via S1 and S2. This allows for convenient installation of the bar type transformer to a busbar installation. This is commonly for installations above 200 amps. The primary is usually rated between 50 to 5,000 amps and the secondary between 1 to 5 amps. The burden is usually between 15 VA for 5 ampere secondary current and 5 VA for 1 ampere secondary current. Cool, important, the secondary must be short-circuited before removing burden while under load. Cool, there's an example of a connection there, and that's kind of what a bar type would look like. So you got the 2 bars coming out of the top. Cool, wound primary type. There's a couple examples there on the right. So the wound primary current transformers have the primary and secondary windings built into the case with 4 terminals for connection. The primary winding has very few heavy turns. The multiple windings in the primary produce an alternating current proportional to the current in the primary. Primary windings are connected in series with the current carrying conductor via P1 and P2. The secondary is connected to meter or resistor via S1 and S2. The standard current ranges are primary between 200 to 1200 amps, 800 amps is common, and secondary 1 to 5 amps. The burden, again, is typically between 15 VA for 5 amps, secondary current, and 5 VA for 1 ampere secondary current. Wound primary current transformers tend to be used in installations with current below 200 amps. And the secondary must, again, be short-circuited before removing burden while under load. That is the most important thing with either a CT or a PT, just because, if you don't, high current could flow in the secondary. Cool. The measurement CTs and protection current transformers are essential in electric grids, with measurement CTs providing accurate readings for metering and normal current conditions, while protection CTs deliver fault current information to protect relays during grid faults. So this is common with for example, your normal motor control circuit or control circuit. You'd have a low current or low voltage switching the coil and the contactor or in this case, a protection device carrying the high current or high voltage. This way, the relays don't have to be necessarily built to handle the massive high current or high voltage of the load or the transmission, but they can control the large contacts or for the switch or the contactor for the high voltage or high current. Does that make sense to you guys? The contactor analogy? Cool. So they're usually an air core type. They have a single primary winding producing an alternating current proportional to the current in the primary. The primary is connected to supply or load through conductor via P1 and P2, and the secondary connected to the revenue meter via S1 and S2. The standard current ranges are primary, normally greater than 200 amps, and secondary is subject to ratio required for the instrument, but normally 1 amp. The burden, again, is usually between 15 VA for 5 amps secondary current and 5 VA for 1 ampere secondary current. Again, the secondary must be short-circuited before removing burden while under load for safety. Cool. So that's an example there of a common measurement protection CT. And there, that's a more diagram view. So you've got the main primary conductor going through the coil, inducing the magnetic field, which then creates a current in those secondary windings. Cool. So yeah, that should clear things up for that question. If you guys get stuck on it when you get to it, you can rewatch the video. Just watch the first part. Cool. So now we'll get into the topic for today, which is the last one in the Transformer series, and then we move on to rotating machines next week. Cool. So we're going to talk about supply transformers. I believe there's a video.
See power at one voltage and delivering it at another voltage. In this way, they help achieve better transmission efficiency while transferring the power over longer distances. In this video, we will go through the working and construction of a three-phase transformer by starting from its simplest form. The basic working principle of a transformer is simple: electromagnetic induction. According to this principle, a varying magnetic flux associated with a loop will induce an electromotive force across it. Such a fluctuating magnetic field can easily be produced by a coil and an alternating EMF system. A current-carrying conductor produces a magnetic field around it. The magnetic field produced by a coil will be as shown in the figure. With the fluctuating nature of the alternating current, the magnetic field associated with the coil will also fluctuate. This magnetic flux can be effectively linked to a secondary winding with the help of a core made up of ferromagnetic material. This fluctuating magnetic field will induce an EMF in the secondary coils due to electromagnetic induction. Since the turns are arranged in a series, the net EMF induced across the winding will be the sum of the individual EMFs induced in each turn. Since the same magnetic flux is passing through the primary and secondary coils, the EMF per turn for both the primary and secondary coils will be the same. The EMF per turn for the primary coil is related to the applied input voltage as shown. As a result, the induced EMF at the secondary coil is expressed as follows. This simply means that with fewer turns in the secondary than in primary, one can lower the voltage. For the reverse case, one can increase the voltage. But since energy is conserved, the primary and secondary currents have to obey the following relationship. Three-phase transformers use three such single-phase transformers, but with a slightly different coil configuration. Here, the primary and secondary coils sit concentrically. Two more such windings are employed in a three-phase transformer. Transformers with high power ratings generally employ a special kind of winding known as a disc-type winding, where separate disc windings are connected in series through outer and inner crossovers. The low voltage windings are connected in a delta configuration, and the high voltage windings are connected in a star configuration. Thus, the line voltage further rises to root 3 times at high voltage side. This also means that from a three-phase step-up transformer, we can draw 4 output wires, 3 phase power wires, and 1 neutral. High voltage insulated bushings are required to bring out the electrical energy. The core of the transformer is made of thin insulated steel lamination. Such steel laminations are stacked together as shown to form three-phase limbs. The purpose of thin laminations is to reduce energy loss due to eddy current formation. The low voltage windings usually sit near the core. Various kinds of energy loss happens while transferring power from the primary to secondary coil. All these energy losses are dissipated as heat. Though usually the transformer is immersed in a cooling oil to dissipate the heat. The oil dissipates the heat via natural convection. Oil in the tank will expand as it absorbs the heat. A conservator tank helps to accommodate for this volume change. To know more on different types of transformer cores and windings, please check out our other videos. Thank you.
Cool. So yeah, that's the basic construction of a supply transformer. Cool. So let's look at it a little bit. So three-phase supply transformers are built much like the normal transformers we've studied already. 2 sets of windings wound around the core. So we'll have a closer look. All supply transformer cores are made out of an iron alloy called silicon steel. This is a mix of iron, carbon, and silicon and gives the metal a higher resistivity while maintaining good magnetic coupling. This high resistivity limits the currents that flow within the core during electromagnetic induction. The core is also split into thin laminations that are insulated from each other. This also raises the overall resistance of the core, further limiting currents. But this also doesn't decrease the permeability. So I don't know if we talked about it enough, but so permeability is the resistance to being magnetized, and resistivity is its resistance. So if we say something has high resistance but low permeability, high permeability, it won't allow current flow, but it will take a magnetic charge essentially quite well. Cool. So here's some parts of the transformer. So you've got a cooling system to one side. You've got the iron core there, and then you've got the high voltage winding and a low voltage winding. Cool. So core type. So a core type transformer is a hollow square shape with each winding wound on opposing limbs. The current flowing in the primary winding and the magnetic field that accompanies it induces magnetic flux into the core. The magnetic flux circles the core and moves through the center of the secondary winding. This then induces current into that secondary winding while maintaining electrical isolation, which is very important, between the primary and secondary circuits. A shell-type transformer may also be known as a windowed core transformer. Both windings are wound onto the central limb. The construction and layout of the windings on a shell-type core allows for greater flux linkage. Basically, any magnetic flux does not get captured by the limb. The windings are wound on, gets captured on the limbs either side of the windings. The flux also gets directly induced into the secondary winding as it's in physical contact with the primary winding, but isolated electrically. Cool. So the position of the windings. So typically three-phase supply transformers are of a shell-type construction. This means that one winding is wound concentrically on top of the other, and both are wound around a single limb. There are three primary windings and three secondary windings that constitute the three-phase configuration. So we'll look into the connection methods shortly. The way in which they are placed on the core is always as follows. The low voltage winding is placed in the core first, and the high voltage winding is placed on the outside. When considering this statement, we must understand that it is not necessarily the primary or secondary winding on the inside or outside. It is the voltage level relative to the other winding. Whichever is the lowest goes on the inside and vice versa. Also pays to note that low voltage does not specifically mean 230 or 400, or high voltage meaning over 1,000. Again, it is purely relative to each of the winding. So you could have a step up transformer. So the low voltage is actually on the inside, which is the primary. So your primary is the inside and your secondary is the outside. Conversely, if it's a step down, the primary is on the outside and the secondary is on the inside. Cool. So there are a couple of reasons that the low voltage winding is closest to the core, and they are insulation. The core of the transformer is fixed to earth to keep it at 0 volts potential. The requirements for insulation from earth on low voltage is much lower than high voltage. It is both cost effective and efficient for the low voltage to be placed on the core first. And then heat. Due to the higher current levels flowing in the low voltage winding, it is fixed closer to the core for heat dissipation reasons. The core absorbs the heat from the windings and spreads it around more effectively. Cool. So if you look at the photo there, that's the typical construction there. So if you look closely at the windings of a power transformer, you would find the high voltage windings sitting on the surface of each limbs, very fine, wrapped around hundreds, possibly thousands of times. This is because the high voltage constitutes low current for the same power transfer. So current in high voltage lines can be very minimal. So low, in fact, that a transformer supplying a small subdivision may only have windings that are the same size as a domestic lighting circuit. The overhead lines that you look at, they don't seem that thick, and that's because they are, but also because usually they're not insulated either. They're usually not insulated and hanging up so high because they're high voltage, but they can be a lot smaller because the current is what creates that heat. Cool. So there are a lot of windings compared to the low voltage because the turns ratio requires a high number of windings on the primary compared to that on the secondary. The low voltage side will have relatively larger windings, which must be large enough to handle the phase current of the secondary load draw. In supply transformers, these can be large copper strips or bars formed around the core. They are then linked to large formed bars to fit onto the output connections. Cool. So then you've got the exterior fittings and connections. So supply transformers often operate at high voltage, and as we know, higher the voltage, greater the insulation values must be. Connection terminals on the exterior of transformers must be highly resistive and stable in all environmental conditions. Often they are made of glazed porcelain or glass and are what look to be interesting shapes sometimes. So actually, I'm going to touch on this for a little bit. So One of the things to note is the design of some of the insulators on the high voltage lines and on the transformers. So I'll just draw it here. So you can see it up here, but more often than not, the transformer insulators, or even on the overhead lines, use the pen, kind of have this. Okay, I'm not doing a very good job of showing it. This domed, I know it looks rather weird. Kind of this domed effect to it. Anyone tell me why that is? So imagine I have an insulator and it just looks like this. So what happens is dust, possibly conductive dust, will build up on this. And so what happens is the water or rain will come down and it'll get in contact with that dust and it'll form kind of a slurry. And then if enough dust builds up, that slurry, depending on what it's made up of, could become conductive. So because it's high voltage and high voltage loves to jump, it could then be conceived that the high voltage could jump up that trickle of water and into the frame of the pylon. So the reason for this is so that when the water hits here, it can't create a continuous path. Let's get some blue in there. So it comes down here, and then between here, it can't continue, and it ends up falling in drops. And those drops are usually separated enough that they can't conduct. So that's the reason why they look like that, is so they can shed water without conducting. That's why your glass insulators look the way they do, the funky cool shape. That's the reason for it. Cool. So low voltage insulators set the connections a small distance off the transformer case, which is earthed. The connections are done by a crimp lug or shear bolt lug. So high voltage insulators are often arranged in stacks or as a single tower. The higher the voltage, the larger the tower to displace the incoming supply from the case and from other conductors in both cases. A conductor travels through the insulator and into the body of the transformer for connection with the core terminals. The reason for the shape of the insulators is to create a longer linear distance for any arcing to occur to earth. Water cannot track in a straight line down the side of the insulator, so a steady path cannot be made. Even if moisture accumulates in the notches of the insulator tower, the length of the pathway is often too long for an effective arc to form. So that's why. You can see from the picture of the high voltage insulator that the conductor on the inside of the insulator is coiled in a spring. That is so that if a fault occurs and the conductor breaks away from the core terminal, the spring tension flicks the potentially live high voltage conductor back up inside the insulator, rather than risking it make contact with the other earth terminals inside the case. Can you guys see that down the bottom? Yeah, cool. Cool. So cooling. So the only limitation to how much energy a transformer can transfer is in its ability to dissipate the heat that it is produced as a byproduct of the transformation process. Transformers are rated in VA or kVA because it can never be accurately predicted that the power factor of a load is going to be. So rating a transformer in VA or kVA allows for a range of power factor values and load currents while still maintaining its temperature within acceptable limits. In order to achieve maximum capacity from a transformer, various methods of cooling must be utilized to keep it cool. while being as compact and efficient as possible. We utilize a number of methods of cooling to achieve this maximum capacity out of our transformers. So we're going to look at those now. Cool. So natural air convection. So the simplest method of cooling a transformer is to naturally let the air around it remove any heat that it is exhibiting. This works for a small transformer up to around 2 kVA. These types of transformers typically are not supply transformers, but purpose for equipment. Portable isolating transformers is one application for air-cooled transformers, or the transformers in your microwaves. I don't know if any of you have seen it, but the videos where they take a microwave transformer, take one of the windings out and replace it with some thick, say 25mm cable, and then you can use that as a spot welder or to melt metal. I've had a few friends do it, and thankfully none of them have burnt their houses down. Oil cooling is the next one. So when air becomes insufficient at cooling, we utilize a mineral oil that transfers heat away from the windings and the core more effectively. Hot oil expands and becomes less dense. As it does this, it rises through the core to the top of the transformer case. As it rises away from the core and towards the cooler casing, it cools off and regains its density again. The cooler, denser oil sinks around the outside of the core then it cycles again. This is effective for transformers up to around 50 kVA, depending on the environmental conditions. You would typically see this type of transformer on a pole top outside a rural property, transforming 11 kV or 33 kV down to 230 volt or 400 volt for a farm. Most of the time, you won't see a transformer that looks like that. They call it the trash can transformer, simply because we don't really use that style here in New Zealand. I've had a couple guys claim that they've got them outside their house, and I went, cool, show me a photo. And then they took a photo, and it was a box, it was a square. If you guys have one or you see one, take a photo, send it through to me, tell me I'm wrong. More than happy for you guys to tell me I'm wrong. Cool. Any of you guys, cool, who knows where their transformer is and what does it look like? Yeah, it's a typical square box looking thing. Big and green, yeah. Hey guys, just remember, the more you talk in the chat, the easier it is for me to mark you guys as present, because that's how I do the attendance. Yes, I can see who is actually in the call, but how do I know that you guys have just logged in, gone away, done something else for half an hour to an hour, then come back? That's purely the reason I ask these questions. Yes, I'm interested in what you guys are experiencing out in the world, but I also want to make sure that I can mark you as present. Yeah, so interesting story about transformers in Wellington. There was an apartment block built up on, not Vivian Street, I can't remember the street. It's near the set of lights as you leave Wellington, just before the tunnel. A big apartment building on the left there. Right outside one of the units is a transformer, and it's got it had to have a fire suppression system installed around it because it was built too close to the building. Originally, it was further away, but then Wellington City Council showed up and went, hey, that's our land, move your frickin' transformer. So they moved it, and then it was too close to the building, so they had to build a fire sprinkler system around it. The people who bought that particular apartment didn't pay for a transformer and all those ugly sprinkler pipes to be in their view of their backyard. So obviously they complained and then took it to Fair Go. I don't know what happened in the end, if they got any money back, but obviously transformers in place, it's hooked up, it's running, they couldn't move it. They couldn't take down the fire suppression system because it was a legal requirement. So yeah, you got to pay close attention to where your transformer's going and yeah, what land is actually yours. Most of the time you put the transformer inside the building, in the basement. I don't know why they didn't do it there. It's usually the most common way to do it. It's hidden, it's out of sight. Yeah, hide the ugliness, and then you can just install cooling fans if you really need to increase the airflow. But yeah. Always nice to know where the nearest transformer is, just in case. Cool. So tubes and radiators. Cool. Once transformers get much bigger than 50 kVA, the surface area of the inside of the case is no longer enough to dissipate the heat generated inside. In order to effectively cool the oil, a greater surface area exposure is required. Transformers are often fitted with external tubes and radiators that the heated oil flows through and is effectively exposed to more of the external environment to dissipate its heat. Kind of like the radiator in your car, but without the fans. You'll see these sort of transformers on the side of the road supplying a subdivision in a residential area or a large installation like a supermarket or a shopping mall. Yeah, big green monsters with fins on the side. Usually they've only got fins on one side. Typically they're rated up to about 1,000 kVA or 1 MVA, 1 mega VA. The cooling principle is the same. The hot oil rises through the center of the transformer and the cooler oil sinks to the bottom. In a tube or radiator cooled transformer, the hot oil fills the tubes or radiators from the top and flows through them to the bottom, being cooled by the air outside as it goes. As transformers begin to approach the upper limits of this transformer type, they will begin to have conservator tanks fitted to them. These tanks are like a reservoir for the oil as it expands excessively at high load. The quantity of oil inside means that if it gets too hot, it must go somewhere when it expands. This tank allows for that. Cool. Fans and oil pumps. So the same principle still applies for these transformers, only natural convection through the tubes and radiators is now no longer effective enough to cool the oil. Fans are mounted to the radiators and force moving air over the fins and tubes to cool the oil faster as it flows. These are powered by a separate supply from the transformer itself, often from a nearby control room, where in modern times their performance is monitored. Oil pumps forcibly move oil around the cooling system. Often they are connected in the section of pipe where the oil is cooled and circulated back into the tank. When used in conjunction, pumps and fans can often double the efficiency of a transformer compared to that of a standard natural oil convection. Cool. So some other not so common methods. So other mediums are sometimes used in certain applications to cool transformers. Water-cooled radiators and tubes are also used in high temperature or high capacity environments. Water is circulated over the radiator fins and then cooled externally to the transformer unit. The cooling is sometimes done by letting the water fall onto a layer of meshes that are exposed to natural airflow or have a fan blowing air over them. This spread of water is cooled much faster than just circulating it in a sealed system. In some instances, refrigerant gases can be used, albeit at a higher cost than standard oil or water. These gases are depressed around the cooling pipes where the heat is dissipated very effectively. They're not the standard way, and the reason they use mineral oil is mineral oil is very non-conductive. You want to use a non-conductive oil because if you use any type of oil that is conductive, you will cause issues in your transformer. Cool. So identification. So outside of the kVA rating, supply transformer are also classified by their cooling systems. They're typically categorized by a 4-letter code. The first two letters indicate the cooling medium that's in contact with the windings and how it's circulated. The second two letters indicate the medium that is used to cool the medium that is cooling the windings. So if you look at the table below, so mineral oil is just O. Non-flammable synthetic insulating fluid is L. Gas, G. Water, W. A, air. And then your circulation method is N for natural circulation. Forced oil not directed, F. Forced directed oil, so D. Cool. Cooling medium, so yeah. So for example, a 350 kVA supply transformer on the side of the road supplying a small subdivision typically sits idle with a small vent of radiator fins at each side. This would be an ONAN type transformer. So oil, O, mineral oil, internally cooling the windings. N, the oil is naturally circulated around the windings. A, air is cooling the radiators on the outside of the transformer. N, the air cooling the radiators is naturally moving around the fins and is not being blown by the fans. So O for the oil, N for natural, A for air, N for natural airflow. Is that making sense to you guys? Sweet. Cool. So another example might be a 10 MVA transformer at a large distribution substation. So it has an oil pump built in and has fans mounted on the radiator system. It would be an OFAF or OFAF type transformer. So O, mineral oil, F, it's forced around the circulation system. A, it's air cooled around the radiators, and F, the air is being forced around the radiators by fans. So if you look at back when we talked about the microwave transformer, you'd be looking at a AF, AN transformer. So air, natural, air, natural. Although you would never usually use those because we only tend to use these for supply transformers. Cool. So smaller transformers, so relatively small supply transformers such as pole top and curbside or berm transformers are generally fitted with protective devices that detect overcurrent and overtemp faults. So thermometers are fitted within the chamber that have an instrument display in the access chamber. When temperatures become excessive, transformers can be fitted with automatic disconnection devices to isolate the equipment and let the transformer cool off before it overheats. Other auxiliary equipment can be fitted to these devices, such as alarms and signals to indicate when a preset limit has been exceeded. So you could have a pre-warning, so you could have halfway to overtemp, yellow light, almost getting to overtemp, red light, and then when it opened and it's too hot, a flashing red light. Overcurrent devices are also fitted to the terminals of some transformers or on auxiliary equipment such as ring main units that control the supply to and from the transformers. These monitor the load on the transformer and operate to take it out of circuit in the event of an overcurrent fault. Cool. So then you've got your larger transformers. So an oil leak on a transformer can ultimately lead to windings becoming exposed and overheating. Too much oil can lead to excess pressure building within the chamber, and the transformer heats up and causes the oil to expand. So the first line of defense for maintaining the right oil levels in large transformer is the conservator tank, which you can see there, the big tank on top. A conservator tank is a tank that is mounted above the transformer and feeds oil into the main chamber using gravity. This tank is sized appropriately to the size of the transformer and is generally filled only about halfway. In the event of a slow leak of the transformer winding chamber, oil can still feed into and around the windings. It also allows for expansion of oil under temperature as the oil level in the conservator tank can rise as the oil expands. The tank is fitted with a breather pipe to allow for air to enter and exit the tank as the oil level rises and falls. Some conservator tanks have an airbag inside connected to the breather pipe so that the oil is never in contact with air and thus lengthens its lifespan. Yeah, the more the oil comes in contact with air, the more impurities get in it and the shorter the lifespan of that oil. Mounted on the conservator tank are level indicators, which indicate the levels of oil within the tank. These can also be connected to alarm circuits to sound off when the level grows too high or too low. And I can never, we can never agree and the tutors on how to say this. The bush holes relay or book holes relay. So I'm going to say it book holes because that sounds better to me. So application. So the book holes relay have been applied on oil-filled power and distribution transformers at least since the 1940s. The relay is connected to the oil piping between the overhead conservator tank and the main oil tank of a transformer. The piping between the main tank and conservator tank is arranged so that any gas involved in the main tank tends to flow upward towards the conservator and gas detector relay. Cool, so that's a cutaway of it there. So the operation, so depending on the model, the relay has multiple methods to detect a failing transformer. On a slow accumulation of gas, due perhaps to slight overload, gas produced by the decomposition of insulating oil accumulates in the top of the relay and forces the oil level down. A float switch in the relay is used to initiate an alarm signal, depending on design. A second float may also serve to detect slow oil leaks. If an electrical arc forms, gas accumulation is rapid and oil flows rapidly into the conservator. This flow of oil operates a switch attached to a vein located in the path of the moving oil. This switch normally will operate a circuit breaker to isolate the apparatus before the fault causes additional damage. The book holes relays have a test port to allow the accumulated gas to be withdrawn for testing. Flammable gas found in the relay indicates some internal fault, such as overheating or arcing, whereas air found in the relay may indicate low oil level or a leak. Cool. So this type, this is an older style type. So these have mercury switches. So what happens is if there's a rapid flow of oil, it heads this way, and then this arm will be forced up, which will force this arm to pivot up as well. And then the mercury will tip back and conduct across these 2 points here, which will trip the circuit. If it's a slow accumulation of gas, the oil level will start to fall. If the oil level falls to where the pivot point is, this arm will come down because of the ball float, and then we'll make contact across the switch there, across that mercury switch. Okay, so this is an older style version with mercury switches. They are still in use around the world and possibly around New Zealand, but obviously as supply transformers are replaced, they get replaced as well.
In this video, we are going to take a look at one of the most important safety equipment of a power transformer known as a Buchholz relay. A transformer is a static machine that primarily consists of primary and secondary windings wrapped around a ferromagnetic core. In power transformers, where voltage and current levels are very high, the core and windings are placed inside a tank to prevent external interference. The tank shields the transformer windings from environmental factors such as dust, moisture, and physical damage, which could compromise performance or lead to faults. This tank is completely filled with insulating mineral oil, commonly known as transformer oil. Additionally, a smaller tank, known as a conservator, is connected to the main tank and placed at a level higher than the main tank. It is used to store excess oil, ensuring there is no shortage of oil in the main tank. Transformer oil plays a crucial role in the operation of power transformers by serving two main purposes. First, Its high dielectric strength allows it to function as an insulating medium, preventing short circuits within the transformer. Second, it acts as a cooling medium. During operation, transformer windings generate significant heat due to electrical losses. The oil absorbs this heat and dissipates it efficiently, ensuring the transformer operates within safe temperature limits. A Buchholz relay is used exclusively for oil-filled transformers and is connected between the main tank and the conservator at a slightly elevated angle of around 2 to 5 degrees. The body of the relay is made of aluminum alloy, and two flanges on the body allow easy connection of the relay to the tubes. Two large inspection windows are fitted on both sides of the relay, housing for convenient inspection. During transformer operation, heat generated due to the resistance of the windings causes the decomposition of the surrounding oil and paper insulation, producing gases such as hydrogen, methane, and acetylene. These gas bubbles rise in the transformer tank and move toward the conservator through the connecting pipeline. Once the gas bubbles reach the Buchholz relay, they accumulate in its housing. This collected gas can be extracted through a gas draw-off valve and analyzed to assess the insulation health of the transformer. Internally, the relay mechanism primarily consists of two floats and magnetic reed contacts, with the number of reed contacts varying based on the relay's design. Each float is carefully designed to respond to changes in oil level or gas accumulation within the transformer.
So this is the more modern type.
On the float is a permanent magnet, which interacts with the magnetic reed contacts to trigger alarms or protective actions. A magnetic reed contact refers to an electrical switch mechanism that is operated by a magnetic field. It is typically enclosed in a small sealed glass tube and consists of two thin flexible metal strips made of ferromagnetic material, which are normally separated by a small gap. These types of contacts are referred to as normally open contacts. When faults such as overloading, core overheating, or insulation breakdown occur in a transformer, they generate an abnormal amount of gas due to the excessive heat produced. Higher gas accumulation causes the oil level in the relay to drop. As a result, the upper float lowers and activates its magnetic switch, sending a signal that triggers an alarm to indicate a potential issue within the transformer. Now, imagine a scenario where the oil inside the transformer begins to leak. As a result, the oil level in the conservator starts to decrease, causing the oil level in the Buchholz relay to drop as well. Initially, the upper float responds to the lowering oil level by moving downward, activating its magnetic switch to trigger an alarm signal. This serves as an early warning of a potential issue. If the oil level continues to drop, the lower float will also descend. Once it reaches a critical point, it activates its magnetic switch, sending a trip signal to shut down the transformer, preventing further damage or catastrophic failure. The Buchholz relay is also highly effective in protecting against serious transformer faults, such as insulation failure or short circuits. When a serious fault occurs, it generates a large amount of gas rapidly. These bubbles move forcefully through the pipe connecting the main tank to the conservator and strike the flap near the oil passage in the relay. The flap, connected to the lower float, is pushed by the force of the bubbles, causing the float to move downward and activate its magnetic switch. This generates a trip signal to shut down the transformer and prevent further damage. And that's how a Buchholz relay, operating on a simple principle, effectively protects a transformer. If you found this video helpful, don't forget to like and subscribe to my channel.
Cool. So that's the operation of a Buchholz relay, and that is the modern version. So obviously the old school version had mercury switches. The modern version uses magnetic trip instead. Cool. So this is silica gel breathers. So these have a special function. So most of the power generation companies use silica gel breathers fitted to the conservator of oil-filled transformers. The purpose of these silica gel breathers is to absorb the moisture in the air sucked in by the transformer during the breathing process. So what is transformer breathing? So when load on transformer increases, or when the transformer under full load, the insulating oil of the transformer gets heated up, expands, and gets expelled out of the conservator tank present at the top of the power transformer, and subsequently pushes the dry air out of the conservator tank through the silica gel breather. This process is called breathing out of the transformer. When oil cools down, air from the atmosphere is drawn into the transformer. This is called breathing in of the transformer. Cool. So during the breathing process, the incoming air may consist of moisture and dirt, which should be removed in order to prevent any damage. Hence, the air is made to pass through the silica gel breather, which will absorb the moisture in the air and ensure that only dry air enters into the transformer. Silica gel in the breathers will be blue when installed, and they turn to pink color when they absorb moisture, which indicates the crystals should be replaced. These breathers can have an oil cup fitted so that the dust particles get settled in the cup.
Today, we're going to look at silica gel breathers. These are installed on electrical transformers. I'm going to explain to you what it is and how it works. Now, silica gel breathers are also referred to as dehydrating breathers or dehydrating breathers. If we have a look, we can see one mounted to the transformer, this section here. And we can see it's connected to what they call a conservator tank, next on the top. What it's actually doing is allowing the transformer to breathe. It means it's allowing air to pass in and out of the conservator tank. So a quick transformer recap for those who don't know. This is a conservator tank, this large cylindrical tank mounted above the main tank. The main tank is this tank here, where all the pointy sticky outputs are. The main tank is there. Now the transformer itself is full of an insulating liquid. This is almost always mineral oil, 95% of the time. As the transformer gets hot, it will cause the insulating liquid to expand, and as the transformer cools, the insulating liquid will again contract. So it has this constant expanding and contracting motion. Now the normal liquid level in the transformer would be around this line here. So imagine an imaginary line connecting these two bolts on the conservator tank, and that would be the normal oil level line, the normal insulating liquid line. And as the transformer temperature increases,
Okay. So yeah, that is a bit of a long-winded video. So basically, yeah, silica gel breather, it allows air into the transformer when the oil cools down and reduces, and then when it expands, when it heats up and gas is produced, it forces that air out through the silica gel breather. But yeah, it's just making sure that only dry air enters and tries to stop any impurities from getting in, because as those impurities get in, it will cause the oil to deteriorate, and then it will stop being as good an insulator and cooling. Cool. So that's our last session on transformers, but what I quickly want to do is we're going to go over the various formulas and calculations that we need to do for the transformers. So we'll just go over those and do a couple of practice questions. Cool. So transformer calculations. Cool. So we looked first at the number of turns versus voltage. So we know that NP over NS equals VP over VS, where the number of NP is the number of turns on the primary side, and NS is the number of turns on the secondary, and voltage, VP is voltage on the primary side, and VS is the voltage on the secondary side. So it's essentially a ratio between the two, and we can use it to figure out current and voltage based on the number of turns. Cool. And then we looked at NP, NS equals VP, VS, which is equal to IS over IP. Cool. So basically we've added IP, which is the current in the primary, and the IS, which is the current in the secondary. And we know that this is the current is inversely proportional to the voltage. So if we step down the voltage, we increase current. If we step down, up the voltage, we decrease the current. Cool. Yeah. Talk to that. So an example. So step down transformer is drawing 1 amp from the supplier at a voltage of 230. Transformer has an output of 12 voltage. We can calculate current drawn on the secondary side. The first thing we do, note our formula, VP over VS equals IS over IP. Then we go IS is equal to IP times VP over VS. Like we talked about, we have to cross multiply with the fractions. Cool, which gives us 0.1 times 230 over 12, which gives us 1.92. So then we can work out the power. So power primary is equal to volts times amps. So 230 times 0.1, 230 watts. And P secondary is equal to voltage times current, 12 times 1.92, which is 23 watts. But we know that transformers are not rated in watts. That's what our load is rated at. Cool. Cool. So let's take a look at some examples. So we have a single phase double wound transformer. The turns ratio of 1,000 to 105. So calculate the output voltage of the primary winding. So VP equals 230 volts. Okay, guys, any ideas on secondary output voltage? Yep, cool. So we'll go through it. So first thing we want to do is we know our formula is voltage primary over voltage secondary is equal to the number of primary turns over the number of secondary terms. So therefore, we can take it and say Vs is equivalent to Vp times Ns over number primary. The reason we do this is because we need to cross multiply when we're doing fractions like this. Okay, so it ends up being voltage primary times number of secondary over, which would be number of primary times voltage secondary, but because we're trying to work out our voltage secondary, we take that out of the equation. So that would give us VP 230 times 105 divided by 1000. So 230 times 105 would give us 24150. But because we're dividing it by 1000, we move that decimal place, and that gives us a total of 24.15 volts. Cool. Does everyone follow how that works? Let's get out of the way so everyone can see it. Okay, cool. All right, I'll leave that there for a second longer. All right, now, next one. Cool. So we have a single phase double wound transformer. We know it has a Vs of 12 volts. And we know it's connected to a supply of 230 volts. And we know that there are the NS is 48 turns. Cool. Have a go at that one, and then we'll go through it. Yeah, we're looking for the NP. Cool. So first we figure out our formula. So the one we need to know. So we're looking for NP over NS equals VP over VS. Cool. Now we need to, again, do our cross multiplication, but we're looking for the numbers primary. So first thing we do, NP equals voltage primary times the number of the secondary over voltage in the secondary. Cool, which is going to give us 230 times 48 divided by 12, which gives us 920 turns. Yeah, that's how you would do that one. Cool. So next one. Cool. So we have another single phase. This one is a step down transformer. It is got a voltage primary of 110 volts. Cool. So we have a volts per turn of 5 volts. Find the number of turns in the primary winding. It's not the same calculation, but it is similar. Yeah, so the way we do this one is find NP. We take our primary voltage and we divide it by our volts PT, or our volts per turn, which is equivalent to 110 divided by 5, which gives us 22 turns. So yet not quite the same as the previous questions. Okay. Yeah, so move on to the next bit. Cool. Then when we looked at measurement transformers, we talked about burden. So burden, so the power used in the burden is basically power. So P burden equals I squared times Z. So current squared times impedance. Cool. So if I just keep the burden of the circuit as low as minimum. So we have a CT connected to the ammeter, has an impedance of 0.2 ohms, and the ammeter to the leads have an impedance of 0.2, and the actual ammeter has an impedance of 0.1. We can say Z total is the same as Z1 plus Z2 plus Z3, which is 0.2, 0.2 plus 0.1, which gives us 5 ohms. So we know P burden is I squared times Z. So 5 amp, we assume it's 5 amp in the secondary when the load is at 300 amps for that CT that we're looking at. 5 squared times 0.5, which gives us 12.5 VA. So that is the burden on the CT. Cool. Then we looked at efficiency. So the basic efficiency formula is percentage N equals P out over P N times 100. That's the basic energy formula, efficiency formula. Then if we look at losses, basic way to look at transformers losses is P N equals P out plus losses. So therefore, N, which is the basic efficiency calculation, include this losses formula. So P out is so efficiency is equal to P out over P out plus losses. Cool. So the following results were obtained during a test on a 1000 kVA transformer. So during open circuit tests, 530 watts were measured. During the closed circuit test, 650 watts were measured at full load current. So calculate the efficiency at full load. If the power factor is 0.7. That's a rather complicated question. So it's a 100 kVA transformer. So it's a 100 kVA transformer. During open circuit, we had 530 watts, and then closed circuit, we had 650 watts. Okay, so that's at full load current. So we can calculate the efficiency at full load if the power factor is 0.7. So the difference in power is 100, this is a bit of a complicated question, so I'll go over it with you guys. Or you can all see the screen. Cool. So the first step, so power equals your kVA times okay. So your power is equal to your kVA times cos theta. That's your kVA. So your power is equal to your kVA times your power factor. Okay? So your power, which is measured in watts, is your input in kVA times cos theta, which is your power factor. So your power out at 0.7, which is your, Z, 0.7 is equal to 100 times 0.7, because we're dealing with 100 kVA, so we'll work it out at kVA. So your power out is equal to 70 kilowatts. Okay. So then we look at your efficiency. So your efficiency, oops, one too many lines, is equal to output over input. Okay. Efficiency is equal to your output over your input. So your efficiency is equivalent to 70. So it's output divided by input. But we can also look at it as, there you go, output. Oh, that's not what I wanted. No, I want never mind, it did work. Wasn't paying attention. Output over output plus losses. So output plus loss. So that means you got 70 over 70 plus 0.53 plus try and get that fit a little bit better. So you got 70, which is your output, over 70 plus 0.53, because our losses are in watts, plus 0.63. Cool, which will give us an efficiency of 0.983, 0.983, 4. Or if we times it by 100, we can get 98.34%. So this transformer is 98.34% efficient. Okay. Is this making sense? So basically, 530 watts were recorded as losses without the contacts closed, and then 650 watts were recorded as losses with the contacts closed. So this is your ion losses, because that's the cost of creating the magnetic field. So once the magnetic field is established, and then this is your copper losses once the load is connected. I know it's complicated. This is kind of a more advanced question that you may get in a capstone or an exam. But yeah, so one thing I will do, guys, because our class is small enough, there is a year 2 theory book or practice book available as a PDF. So what I will do is I'll go through everyone's email address on the SAM system we have here. And what I'll do is tomorrow, not tonight, I'll send you guys out your the theory practice book, and there's got a whole bunch of questions like this for you to have a go at. Okay, so I'll get those out to you guys tomorrow. Cool. Then we looked at regulation. So we looked at how current flows in a circuit. So voltage regulation is equal to voltage no load minus voltage full load divided by voltage no load over 100. Cool. So supply of electricity to installations operating at 200 volts AC. Yeah, cool. So we look at not allowed more than 6%. So the voltage regulation, 230 times 0.6, so 13.8 volts. So your V minimum and max is 230 plus or minus 13.8. So 216.2 V min or 238 V max. Cool. So we have a 410 volt supply. Cool. We are not allowed to drop the voltage in the installation to no less than 395 volts. What is our percentage regulation that we are allowed? Cool. So let's work it out. Cool. So we know our regulation. So our regulation percentage is voltage full load minus, voltage no load. No, I was right the first time. Yeah, no load minus voltage full load over voltage no load times 100. So that would be 410 minus 395 over 410, which times 100, which equals 0.0365, etc., times 100, which is equivalent to 3.66 because it's 658. We need to round up, so we get 3.66%. So that is our allowable regulation for that setup. Everyone following along about regulation so far? Cool. So let's try another one. Cool. Cool. So we have a transformer. It's voltage no load is 230 volts. Its voltage full load is 216.2 volts. Find the regulation percentage. Oh, so yeah, use the same formula. So our regulation percentage is equal to voltage full load minus, no load minus voltage full load over voltage, no load, times 100, which this time is 230 minus 216.2 over at this point 230 times 100, which gives us 0.06, and again times 100 gives us 6%. Oh, that one's nice and clean, easy. Cool. So that's regulation. It's basically your voltage, full load, no load versus minus full load divided by no load times 100. Obviously, if you're not putting much of a load on the transformer, depending on how good your transformer, the regulation is pretty good or pretty bad. You guys will have to do this when you come to do block course. And just because people have been asking in the other class, we'll just quit out of this PowerPoint for a second while I look it up. So block course dates. I was looking at them earlier with one of the other tutors. So for the Wellington area, I'm assuming all of you are in the Wellington area. You just are a bit further away. So right now, year 2 July intake block course. So first one starts on the 28th of the 4th. So that's the 28th of April. And the other one starts on the 12th of May, 12th of the 5th. Okay, so one is the first week after term break, and the other one is 2 weeks later. You guys will be on one of those two block courses. Cool. Carry on. Cool. So then we looked at star delta, and we looked at three-phase. So the first thing we looked at was the star configuration, where the voltage line is equal to the square root of voltage phase, the square root of 3 times voltage phase. So we could then figure out the voltages. Cool. So go. So I'm going to give you a bunch of different values, and then I want you to figure out the opposite. So, okay. So your VL equals 450 volts. What is your voltage phase? Your voltage phase equals 24 volts. What is your voltage line? And then voltage line equals 200 volts. What is your V phase? So we'll start with the first one. When you put your answer in the chat, just put V phase 1, VL2, V phase 3. That's in the wrong spot. Yeah. Okay, yeah, Ollie, you seem to have got your head around this quite quickly. Yep. So I'll grab my pen. Cool. So first one, so your V phase is going to equal your VL divided by the square root of 3. So you're going to take your 450, you divide it by square root 3, which is going to give you 259.81 volts. Cool. For your second one, you're going to take your V phase of 24. You're going to multiply it by the square root of 3, which will give you 41.57 volts. Cool. And for your last one, trying to find V phase, so we're going to divide it again. So it's going to be 200 divided by square root of 3, which is going to give us 115.47 volts. Cool. Is that all making sense for you guys? Cool. So you got to remember, so that's in star. In star, the voltage is affected by the square root of 3, and only in star. But then when we look at delta, which is the triangle, you've got the current, which is affected by the square root of 3. So in star, current remains the same. If you think about it like star being series, so your star current remains the same. And delta, which is your parallel, your voltage stays the same. That's a weird way to think about it. So let's look at a few. So if we're in star, so we've got an I line of, let's go with 12 amps. The second one, we've got an I phase of 33.5 amps. And then the last one, we have an I line of 0.63 amps. Cool. So the first one, find I phase. Second one, find I line. The last one, find I phase. Yeah, so cool. First one, your I phase. So you're going to take your line, 12, you're going to divide it by the square root of 3, which is going to give you 6.93 amps. Then your second one, you're going to take your phase voltage and do the opposite. You're going to multiply it by the square of 3, which is going to give you 58.02 amps. The last one, because it's phase, we're going to take our I line, 0.63 amps, and we're going to divide it by square of 3. It's going to give us 0.36 amps. And we're going to leave it in amps because the question started asking us in amps, and that's going to be the easiest way. Cool. So that's where we'll leave it for tonight. So yeah, expect to get an email from me sometime tomorrow with those theory practice books for you guys to go through. There's a whole section on transformers. Some of the questions you will need to do a little bit of research to answer. But once you have them answered, you can then go through and use that for reference. Other than that, thanks for coming along. You guys have a good rest of the week and weekend, and I will see you guys next Thursday for our next lesson.